Yay! Second one's working. Sorry for that one. I have no idea what happened in the first one, and I can't even stop it. Okay. It's working. I have to test this YouTube thing again. Okay. Yeah, where were we? Predicates. Okay, predicates of other arity. Yeah, like a predicate that takes no arguments is essentially just is like a variable, you know, from Boolean logics. So it's like either true or false. Now, predicates with higher arity, their true or false, or like their true or false value depends on the object you put in them. So yeah, like of course, if you have, you know, predicate values of, my pen is getting dry. This is not good. Okay, so if you have a predicate of arity1, you saw that, you know. This is just saying something about a single object from our universe. This could be, for example, a type. Yeah. Oh. Yeah. So this object is a bee. This object is a, I don't know, policeman. This object is whatever. And then there are predicates of higher arity, which are called, or sometimes are also called relations. So, for example, if we have one like this, it takes two arguments. With these ones, we can describe how elements interact with each other, kind of, right? For example, a relation. So yeah, I mean, you saw that in the assignment. So there was like, you know, we had, you know, bees and birds, or bees and flowers or something. Yeah, where bees or flower is like a type, and this is like a relation of, you know, which bees likes which flowers, for example, right? Essentially, you can also yeah, see them. Nah, okay. There's other ways how to have a look at predicates, but we will make it simple for today. So these predicates with higher arity, they also have they are also essentially like this building blocks for Boolean variables. Only that for them, of course, you need like every combination of x and y. So if we take again our concrete U, or our concrete universe, you have a value for AA. We have a value for AB. We have a value for AC, and so on and so forth, right? So, you know, every combination of objects in our universe. This is also important. They don't have to be different. So you can even put 2 times the same variable in there. Yeah, which is sometimes causes a little confusion. Okay. Now, before we do okay, so there's now only one part missing, and then we can do some, you know, examples and really look at how we can model something in predicate logics. So let me remove this one. I hope you have that in mind, but I need space. Yeah, we can also. Yeah, let me also remove that one. I think we, through technical difficulties, we had stared long enough on this one. Okay, so now we have like these building blocks for these tons and tons of variables. And now we have one final, or one final building block that is important for naming of variables, and that is quantifiers. There is a way to introduce quantifiers without predicates. Maybe we will get there today, but like, so just to have, you know, your image complete there. So yeah, quantifiers. With them we can make statements essentially of the form either for all or there is. So in a quantifier, there's always a variable bound, which is only important for naming of the variables. It doesn't really matter how the variable is named. It's just that if we're using more than one variable, each one has to be bound exactly once in a quantor if it's a sentence. And so in Boolean logics, for example, we were so if we say we fixed our universe to true or false, Q be either true or false, then the question that we were asking in Boolean logics was essentially, do there exist variables x2 exist in xn for how many variables we have, such that some formula phi or something with these variables is satisfiable, or like evaluates it true, right? So if phi is a Boolean formula, yeah, and let's say we only had these true or false elements, then we could say, yeah, okay, is there an assignment to the variables such that our formula evaluates it true, for example? Okay. This is a slightly special case. So this is a little nearer to something called quantified Boolean. So there is something that's called quantified Boolean formula. Boolean formula. Does it? Yeah. QBF in short. That is exactly that. So in this QBF, we actually fix the universe to something, and yeah, then can use these quantifiers to then search for some assignment. Now, in arbitrary predicate logics, these universes are again not fixed. Not fixed for so there we can have, you know, these arbitrarily big ones, not fixed for predicate logic, right? And so, but we can still model something about this, because thanks to the predicates we have, you know, these factories for Boolean variables, and now we can say something about this. Yeah. So, and these quantifiers say essentially for all elements in our universe something holds, right? So if we have some implementation of the predicate, so the predicate knows for which element it's, you know, true or false, then we can state, okay, all of these variables have to be true, or like the statement of here needs to be true. While for the exist case, we just say, okay, for some element x, this needs to hold. And yeah, I think this is best visible if we do it with some examples. The D. Let me make some space here. By the way, don't wait for me. So just feel free to drop whatever questions you have into the into this chat thingy at the side. Because unless you post questions, I will just be here and tell you stories. And when the time is up, I will stop telling you stories. So yeah. So what we did by now is just something that we had in the lecture. And yeah, if you have like additional questions or something that was missing, then please post them in there. There we go. Okay. Yeah, maybe also let me remove this one. So this one is not this one is not from the lecture. This is just to get like a feeling. Yeah. Okay. And we will make now one or two like human language examples, and then I want to get into some more detail of how this. To reopen the book, just a second. At the page. Okay, this example is weird. This one's nice. Okay. Yeah. Sorry, my computer is a little bit slow with loading hundreds of pages in PDFs. Okay. So we say, okay, we let's start with just one predicate, and this is a predicate M, which is arity 1. I think Farron doesn't write it like this, but I prefer writing the arity here. And then we say, okay, M of X means X likes math. Okay. Some people like mathematics. Mathematics. Let me just put this aside so I can see your comments. Okay, some people like mathematics. Obviously means, if we treat our universe, or like, let's say for now we treat our universe as just being consistent of only people, which is not generally the case, but just to make it simpler. So we say, yeah, in our universe there exists a thing that likes math. Yeah, that's easy, right? So somewhere in this big universe, there's someone like math. Now, as I already told you, this is only on the assumption that in our universe everybody is human, or is a people, is a person. So to spice things up, a little, we say we have also a predicate human, which just states X is human. Because in our database, in our universe, whenever we have things that aren't toys, whatever. And now this statement changes slightly, and then it's say, okay, we say that this x that we are searching for not only needs to like maths, but also needs to be human, right? So people like mathematics. So something that is, so our x needs to be a person and needs to like mathematics. Okay, so far so good. Now we have a different statement, and that is, let's say all people like mathematics. So, of course, we need an universal quantifier for this, but now we now this formula looks slightly different. I will write the correct formula first, not to distract you. So, obviously, somewhere we have to post, likes maths, right? Next. So all like maths. But that literally means that every object in our universe likes maths. And now we gotta make sure, okay, but we're only talking about people, so only if that object is a person, then it likes maths. So we're having this implication here in the for all. So question, what would the, oh, this is too deep. So question, what would the statement for all x h1 m1 of x mean? I'm giving the answer because no one's writing in the chat. So this would mean all objects in our universe are humans and like math, which is in general not correct. If we have a universe where there are things that aren't human, then already this part would be in, would be weird, right? So this literally states everything is human and likes maths. Okay. So if you have something in a universal thing, then putting a conjunction here is a little difficult, because we then literally state that everything is whatever, right? Which is not always useful. So usually this notation is used to say, okay, everything that is so for all things it holds that if it is something, then something holds. I brought an example for why this could be interesting in computer science. So let me see, how much space do I have? A little bit. It's fine. Well, let me get over here. So from the practice. Essentially, if you are looking at a program, for example, so you're writing something like, let it be a Java program or whatever, then this is nothing but like a very long string of ones and zeros, right? And what we often want to state is, okay, so we have let's say we have a universe of programs. Doesn't need to be, but like um, we want to define, so if an X is a program, we say we have a thing for C for correct, C of X, which just means X is correct. So our program does not contain errors. However, we also what happens for every program is we first check whether it's syntactically correct. So we have like a compiler that that's essentially what your Java compiler does. It spits out errors when you didn't write the right code. So we also say we have another predicate of p of x. X is a syntactically correct program. And now, of course, we want to state for all x, if our string or whatever is a correct program, right? Then it should be correct. Because if it's not a correct, if it's not syntactically correct, we give it back to the programmer and say, clean up your code first. Right? So yeah, so this would be something. If something is a program, it's correct. Which obviously in practice it isn't, right? So if we had a compiler that could do that, that would be pretty amazing. People are working on this, actually, compilers where if the program compiles, it's automatically correct. But yeah, this we haven't got that yet. But yeah, so this is actually something where like a modeling that happens in practice a lot. Okay, now we have here some nice human language examples. But what always causes trouble is negation in together with quantifiers. And yeah, let me get rid of this one. So, for example, we could say no one likes maths. Obviously a false statement. But, now this could be, so this no one always gives like a little bit of trouble, but essentially we say there is no person that likes math. So there does not exist a thing that is a person and likes maths. All right. Here again, this is an existential, so we probably want to use the end operator. So this is the first statement. It exists, a thing that is a person and likes maths. And now we negate, the whole thing. Which is important. So like, even if you have a non-existent, you'd still probably want to have this end operator done here. Now, an equivalent statement would be obviously something for all. Yeah? So, no one likes math means that for all persons, so we could formulate the same statement as something, for all persons. It holds that if a thing is a person, then it doesn't like math. So, all persons don't like math. So this is the same thing for all x. If it is a person, it implies it doesn't like maths. And let me put the brackets here. So in for quantifiers, it's sometimes good to in a way that the whole statement for which the variable is bound is in a bracket, because that makes it. I think you even have to, because I think a quantifier only binds one predicate, but I'm not 100% sure about this one. Maybe check the slides. But yeah, putting like brackets is always the safer way to go. Okay, so these two statements are both correct. So either there is no thing that is a person and like math, or for every thing, if it's a person, it doesn't like maths. And the reason for these two being equivalent are quantifier laws, for which the negation is very interesting. Let me get rid of this one. So if we have some statement phi, so let's phi be a sentence. Then we have for all if you have some statement, if something holds for all x, whatever that statement is, right? And we want to negate this one, so something does not hold for everybody. Something does not hold for everybody. We know that there's a counterexample, right? So there is something where it doesn't hold for, and that's why this is equivalent to there is something. There is an x. That's a counterexample, meaning for which the statement does not hold. Yeah. Maybe put a little bit of a border here. Okay. Likewise, if we have there exists an x such that if there exists something for which our condition holds, what we want to say it doesn't exist, that obviously means it holds for everything, right? So for all x, but we then have to say for all x this is not true, because if it were false at some if it were true at some point, there would exist something, but there exists. We want to say that it doesn't exist, so we put for all x not phi of x. Yeah. So when negating something with a quantifier, we change the quantifier from we swap between for all exists, and we put the negation in front of our statement. So as we can see that here, let's do this step by step. So okay, so we have negation and then some quantified sentence. So we do exactly that. With a negation, the exists becomes a for all, for all x. And then the inner statement is negated. That's important. So not p1 of x and yeah. So the x is a person. So for all x it holds that is not the case that p1 is that x is a person and x likes maths. Okay. Yeah. So now we resolve this negation over here. So we have for all x, it holds. And now De Morgan's laws, really important. not p1 of x, or, yeah, important, this is an or over here, or not m1 of x. So for all x, it holds it's either not a person or it doesn't like maths. Right? And then, just for the sake of beauty, we know that we can express an implication with an or with the following really useful rule. So if we have A implies B, this is equivalent to either not A or B. So either our premise is false or B holds, right? Same thing here. So just in reverse, we have an or, and then we say for all x, if it is a person, it doesn't like maths. That these two statements are equivalent. Okay. So the tutorial time for today is technically over. If you want, you can still visit me. I'm currently in the COFO building on the second floor. I think room 208 or something. Yeah. And then you can keep on asking questions. Save this live stream. So if I press end stream, then this live stream is being recorded, and you can watch it anytime from home. And I will keep it on for a while at least, and then you can rewatch it. Okay. And thank you all for coming here. Please give me some review of how reasonable making such live streams is. I mean, for me, it's a hobby. Like, if there is if you kind of like this, I might do that from time to time. And if you have questions, just write me or something. And hope to see you again. Bye bye.